much.
All right, I'm going to get started. So how are you guys doing? Everybody doing all right?
Good so far.
Good so far. So this is our second day of Extragalactic. So here's what we're doing today. I forgot to put a due date on the survey, so a couple of you did not do it. I have made another due date, and it is now due Monday. If you didn't do it, please do it. It's useful for me to see, who you are, and like if you've, because I'm gonna ask you like 500 million times if you have seen Thermo or whatnot. So there are things that I'm gonna ask you guys, kind of as a collective. But if I can see what you all did, like how many classes you've taken and where you're at, that's really useful for me. Also, there's a bit about what you want me to know about you, and I find that very, very useful because I feel like I learn about you guys that way. So please do that if you hadn't. The notebook. I'm not going to go over the notebook in crazy detail because that's why I wrote the notebook, so that you can go through that and read stuff. Is there anything about the homework notebooks that you guys want to talk about in particular? I'm gonna fire it up. Yeah.
So then I was able to like turn it in again
Yeah.
the proper way.
Okay.
But I saw that it's just like, how do I say this? Just like a tiny little window when I looked at it. Is that how it's supposed to look when I turn it in?
I'm not sure. I've never turned in an assignment.
I'll show you later.
Yeah. Okay. We can talk about it later. So let me fire up the thing, and I'll just run through it real fast. Where we're at? Okay, here we are. So, almost everybody turned in something that looks like they did it right. A couple of you missed it, but the only thing that I really want to spend time on is showing you what I want you to save. So you do a bunch of stuff in this file. So you did some stuff in this file, and then when you save it, you just save it here. It auto saves so that you can't. So there isn't a save and checkpoint is the button you want. So do that. It writes to that file that you downloaded. So you downloaded a file that looks like. I leave mine in Dropbox. That way, if this computer falls off a bus, I don't care. So you downloaded a file that looks like this. You then open it with Jupyter. And if anybody's still having trouble, swing by. We can do it after class. We can do it later. Either is good. I then do some stuff and I save it. It saves it right back in this file. So then when you go back to upload it, I can't go to Canvas. You go to Canvas and then there's got to be a file upload button. You just upload that file and it'll just make a blank. Like I don't ever see what it posts. I just download everything. So I'll download that file and I'll look at your file directly. So I don't know what it looks like in the submissions on Canvas, but that's basically it. And these will be relatively painless, relatively. Yeah. So there's a bunch in here, and we'll come back to this document from time to time. And you should as well. When the homeworks come up, you should go pull up this thing and remind yourself how lists and dictionaries and stuff work, because we'll be working with all those objects. Yeah. Any questions? I'm gonna stop for a second and let you ask questions. Yeah.
Can I resubmit it if I feel like I submitted it wrong?
Yeah. Yeah. If you didn't upload this file, you can go ahead and do it again. It doesn't really matter if you don't. I already gave you the points. So, because I could see what you did. It's just easier if they all look like this. So, I cannot tell how hot I am right now, which is a fascinating problem. It's kind of cold. It's usually pretty warm in this room, so I'm usually sweating my butt off. Okay, notebook. And then we'll get to the lecture. There's a reading that I posted. It's due Monday. There's a homework that'll be over what I do today and what I do Tuesday. That'll be due next Wednesday. Mostly stuff today. Hopefully those will all be up. Also, if I ever say I'm going to post a homework and then you don't see it, I would appreciate it if somebody would tell me, because every now and again I flake. I try to not, but and then nobody tells me, and I'm like, oh no, we got homework that was supposed to be due now, but I got to do something else. So I am kind of a space cadet. I hope everybody's okay with working with me on that front. Okay. Then we're going to talk about stars. Most of the information that we get about outer space comes from starlight. All of this stuff that we're going to talk about today is kind of foundational stuff that we're going to need later on. So if anything that I say today doesn't make sense or you want to talk about it more, I'm happy to. Please stop me. Also, I think that all of this stuff is stuff that you've seen in previous classes, so I'm going to kind of go faster than I do often. So let's see. Oh, hey, that's a slide from last year. So when I say massive star, does that mean anything to you? What does massive star mean to you? 8? Okay. What else?
More than 8 solar masses.
8 solar masses is a good lower limit. What else? What do they do? They go off in supernova. They go off in core collapse supernova. They go off in a particular kind of supernova, but all of those guys blow up and turn into supernova. What else are they? What do you know about? Luminous. Yeah, very luminous. Why are they luminous?
Because of how big they are.
Because of how big they are. More mass, more energy.
More stuff in there.
Yeah, more gravitational energy being released. So a star is gravitational energy being released. So more mass, more hot, more bright. What else?
Heavier elements.
It makes heavier elements. That's right. What about what happens when they're burning so hot? What does that mean for their lifetime? Short. So they live for not very long. So like 40,000 Kelvin, short life. UV photons, that's the one last thing that I was thinking. Because they're hot, they give off a lot of ultraviolet photons. And this is going to be a running theme. We're going to talk about these UV photons quite a lot over the course of the semester. They're rare. I'll talk about how rare in a little bit. So we'll talk about that detail. They're usually blue. What do I mean by blue? My shirt is blue. My shirt is 2 kinds of blue. I mean something pretty specific when I say blue. We'll talk about color today too. Bigger than about 8 solar masses, and they make all the metals, and they make all the explosions. They don't live very long. They explode pretty fast. And they're very, very useful. Okay. Massive stars are, I don't know, they're some of the most useful objects because we can learn a lot about them. They're very bright. Anyway, so okay, today I just wanted to set that stage and talk about physics for a little bit. So today I'm going to real quick talk about redshift, and the only reason I'm going to do that is because I'm going to forget to define it later, and I'm going to use redshift like a word. And even though we're not going to get into cosmology for a couple of weeks, I'm going to spend a minute talking about distributions, and this is just math, but I think everybody needs a little bit of practice working with distributions, and we'll do it several times throughout the course of the lecture. I'm going to talk about 2 kinds of photons, thermal photons and line photons. There are 3 really kinds of photons that you can have, and I'll talk about all of them. Well, okay, a photon is a photon. I mean, the photon doesn't care where it came from, it's just a photon. But I care where it came from the spectrum. So I shouldn't say 2 types of photons, I should say 2 types of spectra, but we'll talk about that in a minute. Then we'll talk about stellar classification. We'll talk about the scalings and distributions of stuff. Then we'll talk about the magnitude system and all of the things that come out of the magnitude system. There are several things that look like magnitudes that behave a little different. The distance modulus behaves like a magnitude. Color behaves like a magnitude. Magnitudes are kind of fussy, so we'll talk a little bit about that. And then we'll talk about filters, which is combining distributions and magnitudes. And then HR diagrams. I'm not actually going to talk about metallicity today. Okay, what is redshift? So space is expanding. Everything in the universe that's out past about Andromeda is moving away from us pretty fast. Now, if you think about, have you ever seen a scissors lift? It's a cart. I have this picture in a different slide deck, and I get here and I always forget that I didn't put it in here. So a scissors lift is a truck that looks like this. Does that make sense? Has everybody seen a truck like this, like floating around in a mall or wherever? And this goes up and down, and this goes up and down by these two things contract, and it makes this thing expand. Now, if I think about making this thing, okay, make it very long, but it doesn't really matter if I make it long or not. I think about if I think about being right here, and this thing is going up, let's say it's going up really quick, because this guy likes to have a good time. So it's going up really fast. The velocity of the joints of the scissors lift, this one is moving faster than this one, right? That makes sense? This one is moving at a speed 1. This one is moving at a speed twice that. And this one is moving at a speed 3 times that, because this one is being accelerated by this distance getting shorter. This one is getting moved upwards by this distance and this distance getting shorter. So this thing, let's number these. 1, 2, 3, 4. This guy is moving with a distance of v. This guy is moving with a distance of 2v. This guy is moving with a velocity of 3v, and this one is moving with a velocity of 4v. That makes sense? Because this thing is moving by itself, and this thing is pushing it. This one is moving by itself, and the next one is pushing it. So the further away you get, the faster the velocity is of the actual object. And outer space works like that too. So in space, oh, I forgot to switch the camera. No, man, I totally lost my great drawing. There was an amazing drawing here. You missed it. So space is expanding. So if I have 2 points in space, since everything is expanding, if I have 2 points in space that are moving apart with a distance v, a thing that's twice as far away is going to be moving with a distance, with a velocity. I've said that like 4 times now. I have no idea what's going on. Velocity. This is moving, its distance is twice, so its velocity is also twice. The whole universe is like that. We'll go through this in detail when we get to cosmology, but the upshot is that the velocity that something is moving away from us is this constant number times the distance, which is kind of awesome. And what that means is that if I'm sitting here, then I've got some object here, its photons are redshifted away from me because they're stretched out by the space. Now, slightly different from Doppler shift coming off of an ambulance, because this is actually about the stretching of space more than it is about the velocity of the object. That's a subtle point we'll come back to later. So everything is moving away. Further things are moving away faster. If I talk about the redshift, we're going to call this z. This is the change in frequency of a photon relative to its rest wave. This is f observed minus f emitted divided by f, just the fractional change. This is what the redshift is of a photon coming off of this galaxy over here. Let's say that I'm at this galaxy here, and here I've got another galaxy that's moving away from me. So redshift is how much the photon got shifted. Ft, make that not look filthy, shift. So it's the amount of shift. It's also the velocity. It also gives us the velocity of the object. We usually don't need that very much, but it gives it to us. It gives us the age. And it gives us the distance. So when I say high redshift, high z means a bunch of things. It means it's far away. It means the frequency of the spectrum is shifted to longer wavelengths. It means it's moving very fast. But again, that velocity doesn't do anything for us. It's so far away, we're not in any kind of causal contact with these objects. But it's there. It means that the object is young. and the photon is old. So a high redshift object hasn't been around very long because we're looking at an earlier part of the universe. So high redshift objects are earlier in the universe. So try to keep all four of these things in mind whenever a redshift comes up. Yeah.
Sorry, could you explain the object is young, photon is old thing?
Yeah.
a little more?
So, this is time. This is redshift. A redshift of 0 means that the photons haven't been stretched out. That's right now. So the moon is at a redshift of 0. The Large Magellanic Cloud is at a redshift of 0. Andromeda is the only object really with a negative redshift. So we kind of ignore that one. Really, we need to talk about things that are a little further away. So things that are close, here's my universe. So here's me at the center of the universe. Now, because the universe is infinite in all directions and homogeneous in all directions, I could be the center. It doesn't matter. The church loves this. So this is a redshift of 0. A redshift of 1, remember z equals delta f over f. A redshift of 1 means that the photon has been shifted by itself. So that means space has doubled in size. Does that make sense? So redshift of 1 is back here, and that's, let's say, here. So objects here, those photons were emitted not super long ago, half the age of the universe, kind of a while ago. Now, there's not a direct, actually, I don't want to write this as time, I want to write this as redshift. Because the relationship between redshift and time is a little complicated, we'll get to it later. A redshift of 2 would be down here, and that's saying out here. And a redshift of, say, this is not a linear axis, 1100, to pick our random one, is out here. This is pretty close to the beginning of the universe. So when I see an object that has a redshift of 1100, I know that the photons were emitted close to the beginning of the universe. So that means the object that emitted them is pretty young, relatively. But the photon spent all of this time travel to get to me. So that photon came from early in the universe. The object that you're seeing isn't very old. Yeah.
So when you're saying the object that you're seeing like at the time when the photon was emitted from that object?
Yeah.
Okay.
Yeah, so you got the time when the photon was emitted, and that is given by the redshift.
And then what you see is a young object.
Yeah,
when
you see the
look at it.
baby pictures of an object. That thing goes on to do other stuff. We don't get to see that. But now it's off doing other things, but we're not going to see those photons for another however long. Okay, we'll come back to this. Does anybody have any questions on that real quick? This will come back again. Mostly I just wanted to tell you about all the things that I mean when I say high redshift. There's a lot of baggage that goes along with that. Okay, now we're there. Where's my control? Okay, distributions. Let's talk about distributions for a second. So a distribution is a mathematical thing that is, kind of straightforward to deal with, but until you get a little practice, it's kind of weird and annoying. So let's pick one particular distribution. So what is a distribution? Oh man, I had a math grad student in my class last semester, and he totally called me out on all of my not particularly rigorous mathematics. That is how it works. I'm a physicist and I do physicist math. So we wave our hands. A distribution has a lot of rigorous mathematical backing. So there's a lot of interesting math that goes behind this. This is my pulling it out of my pocket math. A distribution is the. Also, I can't spell, so I apologize. The amount of stuff So a distribution f, let's say f of h is a distribution, then f of h dh is the amount of stuff at h and h plus dh. What do I mean by that? So, okay, let's pick one. So let's say that this is f of h, and this is the height of people in the United States. What's that look like? Well, there's the most probable. What's the median height? Like 5'11" for men, and like 5'10" for men, and like 5'6" for women, I think. Is that right?
I think it's
Actually,
5'4".
no, I think it's short. I think it might be 5'8".
Okay. Anyway,
It's like 7.
these are all very little deviations. So we're just going to call this, I don't actually know what it is. I'm going to call it capital H. Capital H is the mean, and we'll just pretend that there's only one kind of people. Maybe we're looking at all people, men and women. H is the mean for all people, so it's going to be like 5 or something like that, right? So we have some maximum, and we know that, okay, so if this is H, this is like 5'5" or something that's thereabouts, 5'5" thereabouts. If we go down here to 2 feet, we don't have very much. And if we go up here to 7 feet, we don't have very much. You know you've got a nice curve that connects those things. So I can ask, how many people have this height? 0. Why? Because this is continuous. How many people have this height plus or minus 1/4 of an inch? That's a question that you can answer. So you've got to integrate. If you have a distribution, the distribution by yourself doesn't tell you much. The integrals of the distribution would actually give you real information. So if I want to know first, how many people are there? This is the integral of f of h dh. This just tells me how many total people are in the population. Now, I could have a probability distribution, a PDF, in which case the integral of the distribution isn't the number, but it gives you 1 because you just divide it by the number. So that's an easy thing. So sometimes this is just 1, but usually it's n. Usually. Ignore that usually. Sometimes it's 1, sometimes it's the total number. We'll go with a plane distribution for now. So the number of people in the country is just the integral over the distribution of people. What the distribution tells me is how many people I have in this little window. So if I have a window that's centered at 5'5" and has a width of, let's say we go from 5'4" to 5'6", the number of people between 5'4" and 5'6" is the integral from 5'4" inches to 5'6" inches f of h dh. That tells me how many people are within this range. Now, okay, what I want to ask is how many people are 5'6". That's a meaningless question because we're now talking about absolute precision. Nobody is exactly 5'6". They're 5'6.0000001. This is the kind of, this is calculus, so you've got to be careful. Nobody is exactly there, but if you have a little window, even if that window is infinitesimally small, even if it's very small, you'll have a finite number. So distributions are about counting stuff. It also gives you statistical information about stuff, and this is where the power really shows up. Say I want to know what the average person is. We all have a rough idea of what the average is. How do you find the average in general? Somebody else, something.
You add them all up and divide by the number you have.
Yeah, you add them all up and divide by the number you have. And that's what we'll do, but we'll do something a little differently. So one way to say it is H is the sum on HI divided by N. Now this is if I take every person and I count them. I don't necessarily want to integrate over people, I want to integrate over height. because it's easier. Because I don't need to know how many people there are, I just need to know what the distribution is. I don't need to know the absolute number, and I don't need to go ask every single person, I just need to know what the distribution is. So instead, we'll use the distribution. H, the average height, is the integral of H. So we're going to integrate. So we're going to march through heights from the smallest height to the biggest height. So let's say we'll go from 0 to infinity. That's a fine thing to do because the distribution goes to 0 and 0 and infinity, so it makes sense. H times f of h dh. This is the average of the distribution. So what you're doing is just saying, I'm going to count each height and multiply by the number that I have at that height. So it's just like adding them up and then dividing by the number, then you've got to divide by the number. This is just adding up all the stuff. So that's pretty useful. That gives you the average of the distribution. Not always the peak of the distribution, because sometimes if you've got a really long tail, you might have like really ridiculously large objects that throw off the average. So the peak and the average aren't the same. Both are useful. We'll talk about those details in a minute. One of the things that I need to know is how broad is this? How wide is this distribution from, say, here to here? Or say from here to here? One way to do that is to get the standard deviation, which we'll call sigma. And this, if you're doing it by hand, is going to be 1 over the number times the sum on h, each height, minus the average squared. So the standard deviation is you march through everybody, you ask what their height is relative to the mean, you take the difference, you square it. Why do I square it? What would happen if I didn't square it and I just took this average? The sum on hi minus h over all my objects.
Signs would be different.
Was that?
The signs would be different.
Signs would be different, so what is that average? You can tell me what it is right now. Yeah, whenever I'm looking for a number, and it's usually 0. So if I just do this sum by itself, I just have sum on hi minus big H squared, and then 1 over n. I'm going to forget the 1 over n all the time. I apologize in advance. If I do this, then here's my height. My points are defined on either side of this, but they're symmetric. So every time I've got one on one side, I've got another one on the other side. And so if I don't have the square, this adds up to exactly 0. Another way to see that is by saying 1 over n times the sum on hi minus big N equals 1 over n sum on hi. This is the average that we just did, minus the sum on n, or n. These both give you 1, so this gives you 0. So basically, this is symmetric. I don't know if that was helpful. This is symmetric. H is the center. We defined it that way. And all our points are going to lie on either side. So if I just add them all up, I'm going to get 0. So that's not very interesting. So we square it so that we have positive things. Yeah.
So does non-squaring it tell you anything about like non-symmetric distributions?
Say that again?
Like if we have a non-symmetric distributions?
No, the way I described it is always going to be 0. Even if this distribution isn't symmetric.
Okay.
H is at the centroid. So if I've got a distribution that has a long tail like this, H is going to be here in the middle, so everything's still going to cancel, even if the distribution itself isn't symmetric about its peak or about its midpoint. That's a good question. We can also ask, so how do I get this from a distribution? I get this from a distribution just like this, sigma squared, squared, that's sigma squared. Another thing that I often forget. This is the squared. The standard deviation is the squared of this. So this is actually the variance. Everybody's kind of sloppy with that terminology. So sigma squared is equal to the integral 1 over the number the integral from 0 to infinity of h minus big H squared f of h dh. So this is where the distribution comes in. Instead of a sum over people, we're having an integral over height, and then we need to know how many people are at each height. So then we're just adding up the heights. Okay, this is kind of an obvious example, and I feel like that makes a lot of sense. It'll get muddier when we get to more complicated distributions over more complicated structures. Does anybody have any questions about? Yeah.
So were they both? Which one's the squared one?
They're both squared.
Oh, they both are.
Yeah, these give you the same thing.
Oh, gotcha.
They're both squared.
Makes sense.
Yeah. So distributions are very useful, and they're tools to get stuff. And they tell you about where the stuff is distributed in the system. So we'll talk about the distribution of photon energies versus wavelength. We'll talk about a distribution of masses. We'll talk about, I guess the black body is a spectrum. So we'll talk about several different distributions today. Yeah, and they underpin a lot of stuff. So in quantum mechanics, when you get there, the wave function squared also behaves like a distribution. And part of what makes quantum hard is getting your head around distributions in the first place, as well as all the weirdness of quantum mechanics. So we'll just talk about distributions now. Get that out of the way. So this will show up again, and again and again. So stop me and ask questions if you get confused about things. How am I doing now? This class does not end at 12:30. It ends at 12:50. I got really stressed out that I was way behind. Yeah.
Do you mind explaining that one again?
Yeah. Yeah, so the variance, sigma squared, is equal the sum on hi minus h squared divided by the number. So this is the variance that you've probably seen elsewhere. Well, let me, if you want to get that from a distribution, so doing it this way requires having the height for every person in the United States, which is tricky because there's some people out in the middle of Alaska that don't want to talk to me. It's data that's hard to get. So we need the distribution so that we can infer that information. It's again 1 over n. And then we're going to, okay, so this is a sum over I. This is a sum on people. We're going to do the same thing. H, now I don't subscript it by I because it's a continuous variable, but it's the variable. H minus big H, the average, which we defined over there. And we're going to square it. dH. Now this is a sum over height. Oh, I'm sorry. F of h dh. F of h says how many at each height. So it's the same thing. So if I'm going along and I've got, like, say I've got 30 people that are 5'5", and 34 people who are 5'6", and 38 people who are 5'7", I don't need to do 35 plus 35 plus 35 plus 35 plus 35. That's boring. I just say 10 times 35 and 8 times 36, or 5'6" or whatever. So I don't want to count everybody. I can just say I've got 500 people with this height, 600 people with this height, 700 people with this height, 500 people with this height. So we'll just say how many people are here. We'll multiply the square by that, and we'll integrate. So you're integrating over the whole population and asking about it, but in one you're asking about every person, and the other you're asking about every height. Does that make sense?
I think so.
Okay. we'll come back to this again, and if it's still confusing in a little bit, yeah, we'll have another example in about 8 seconds. Kinds of photons. So there's basically 3 kinds of photons that astronomers distinguish. Now this is an oversimplification. This isn't like formal classification that people use, but it's the terminology that people use. So there's continuum photons, and these are photons where the distribution of photon wavelengths is broad. And these usually come from thermal processes. So anything that's got a temperature emits photons. Everything emits photons. No, that's not true. Cold hydrogen doesn't. Lots of stuff emits photons just because they're moving around. Some things emit photons because something changes. So like if I've got a hydrogen atom and it goes from the second excited state to the first excited state, that change in energy has to come with a photon because energy is conserved, right? So the atomic energy changes, it has to spit off a photon or get a photon. Those photons are only at one frequency. That's very different from the temperature of your body or the spectrum that your body gives off, which is going to have a bunch of different frequencies. So we'll talk about this bunch of different frequencies in a minute. We'll talk about lines shortly after that. So lines are narrow distributions. So again, these are about distributions. The continuum is a broad distribution, so lots of different wavelengths are produced. Whereas line radiation, only a few wavelengths are produced. And this is useful for a lot of reasons that I'll get into. There's also non-thermal photons, where usually something ultraviolet is happening, like a star is exploding, or something is changing very quickly. And those are different from the black body photons because they're not in equilibrium. And when you take StatMech, you'll understand that equilibrium is something we can talk about, and non-equilibrium is very, very difficult to actually do any physics with. But those are pretty rare. Those are usually come off in the X-rays and the gamma rays. Though sometimes there are thermal X-rays. So let's talk about the continuum photons first. So we're going to talk about the black body. So how many of you have heard of the black body at some point in time? How many of you? Okay, everybody here. Sweet. So let's see. What is it? What does it tell you? Somebody yell something about the black body. That's a harder question.
I mean,
Analyze.
I'm not sure if I'm right.
So a black body emits all the energy it absorbs. What'd you say?
No, I was gonna say I'm probably wrong. I thought that it just like absorbed everything.
It doesn't absorb everything. It absorbs and spits out.
Okay.
Somebody yell something else out about.
It's an ideal spectrum, emission spectrum.
Right, it's an ideal emission spectrum. Yeah, those are good things. So it's the distribution of photons coming off of something in thermal equilibrium as a function of either wavelength or frequency, depending on how you write it, because those are related. It's only a black body. So, okay, let's talk about what it is. So this kind of throws everybody off a little bit because it's kind of a weird cartoon, but a black body is a thing with a temperature. So one of the original, okay, when you're at a party and somebody asks you, why do I care about quantum mechanics? Thank you. Somebody asks you, why do I care about quantum mechanics? You can tell them that quantum mechanics is necessary to understand why your oven is the temperature that it is. It's necessary for your phone to work. But the phone, that makes sense. I don't understand crap about what's in the phone. Of course, it's quantum mechanics. It's magic and fairies. I don't know what's in the phone. I don't know how that works. But my oven, it's just fire in a box, right? So your prototypical black body looks like this. So it's just, here's me. I'm seeing into some cavity that has some temperature. Any photons that go in are absorbed and just give me more temperature. So the prototypical example that you probably saw in modern or whatnot is an oven like this, where you can see into a hole, and so all the photons coming out are coming from the thermodynamics. This is more useful if you're trying to understand, say, a cloud of gas with some stars by it. Well, actually, as a tangent, I'm not going to go. Sorry, squirrel brain decided it wanted to talk about that, but squirrel brain can shut up. So a black body is a thing in equilibrium. And that's the important bit. So when you studied it first, there was all of these rules about what a black body is, about emission and stuff. The important thing, the thing that really matters, is what you're looking at is the temperature of the object, and not light reflected off of something that's nearby. So if I'm trying to understand the spectrum of one of these lights, I have to understand the photons that are coming off the light, but also the stuff that's reflected off of that light from the other lights. That's not a black body. It's also not a black body because it's a fluorescent light. It's produced by line radiation, but that's different. So a black body is a thing in equilibrium. And that's the important bit. And what you're seeing is the temperature of that thing. That's when you have a black body. Now, how does a black body work? Why do they need to develop quantum mechanics for this? Well, because it turns out if I have a thing that's hot, say I've got an oven of a certain size and I have a thing that's hot, and I want to talk about all the wavelengths of photons in there, I can't have whatever wavelength I want. The wavelengths have to be quantized to fit in the box. And that's where quantum mechanics came from. And then all of this other weirdness came from that. So what does it look like? So this is the formula. B, I'm going to, B stands for black body. It's a function of lambda, and it's parameterized by a temperature. Now, this gets written all kinds of different ways. Sometimes it's B lambda T, sometimes it's, anyway, this is the way that I wrote it this time. So B is a function of lambda, and it's parameterized by a temperature. And it's equal to, let's see, 2hc squared over, that's just a number, I don't care about that. Lambda to the fifth, I care about that. And then this kind of complicated bit, 1 over e to the minus h nu, oh, come on, no, h, I'm writing it as a function of lambda, hc over lambda kt minus 1, all of this to the minus 1. This bit, let's talk about this bit. Okay. E to the minus h, I'm going to write this a little differently. H nu over kt. Yeah, I wrote it up here as hc over lambda kt, because I have to, but that's a confusing way to write it. Let's write it a little differently. Let's write it as e to the h nu over kt. What's h nu? Nu is the frequency of the photon. So what is h nu?
Or the energy.
The energy of the photon. So that's something that you should like really drill into your head. Frequency is energy, because that's going to help. Frequency is energy. H is just units. H isn't magic. This is just, we wrote the units down wrong. Right? Frequency is energy. KT, what is KT? What's, yeah, K is the Boltzmann constant. What is K times T? What is the Boltzmann constant? Does anybody know it off the top of their head? So K Boltzmann is like 1.6 times 10 to the, I can't remember what the actual number is, ergs per Kelvin.
That's just energy.
So it's just an energy. K Boltzmann turns thermal energy into an actual energy, turns T into the thermal energy. So this term, e to the h nu over kt, this is e to the photon energy over the thermal energy. And there's a minus sign there. This is called the Boltzmann factor. It tells you if you've got an energetic event, how likely is it? I'll vary. Usually goes down like an exponential. So this term, in general, e to the minus delta E over KT will show up a whole bunch this semester. And it shows up in the black body down here in the bottom. It tells you how likely you are to have a photon at that energy. And then you do some more work to fold it in like this. Deriving this takes statistical mechanics. I'm not very good at it. But this is the shape. And then there's this lambda to the fifth out front. I don't have a good heuristic argument of why this is lambda to the fifth. Maybe I should. Oh, my camera's not on the right spot. Oh, there you go. So we have this distribution, and this is in, what are the units? Let's talk about units for a second. Let's talk about the units of the black body. I'll come back to that in a second. Okay, so this is a little confusing. The black body is what? Number of photons per second? Not quite. So what I want is the energy versus wavelength. I want energy here. But I want the most generic energy that I can come up with. I want the energy that only talks about the microphysics and not the structure. So if I take a star that has some temperature, and then I take another star with the same temperature, and I put it next to it, then I have twice the energy coming off. I don't want that. If I have my telescope, and I can only see this much of the sky versus the whole sky, that changes how many photons I get, right? The amount of sky I see changes the number of photons I get, so we need to get rid of that. If I make my collector twice as big, I get more photons, we need to get rid of that. Does that all make sense? So, and this is energy, we're gonna bin it in terms of wavelength. So this is a function of wavelength, and this is energy, but it's energy per second. Okay, not total energy, it's power because we need the photon count. So this is energy per second. So this is an ergs per second per wavelength, steradian, which is the solid angle. I'll talk about what a steradian is in 2 seconds. Per area, per centimeter squared. So this is the number of photons per second that my star spits out in each little wavelength bin over the whole sky, over the whole surface area of the star. So there's several bits that go into this. Another way to think about this is if I've got a detector, I want to get rid of all of the kind of boring detector parameters. So the boring detector parameter is how big I make it and how big my opening angle is. I just want to know about the ergs per second generically. So we divide through by the collector area, we divide through by how much of the sky I see, and we divide by wavelength beam. So this tells me the most generic thing possible about what the photons are doing. So now this tells me, so okay, this is kind of hairy, and I often don't care, and I just care about the ergs per second and the fact that it's, so I'll get a little sloppy with this sometimes, and I apologize in advance. So these are the units on the black body. So it's ergs per second, that's the most important bit. Per centimeter, because we're gonna make it a distribution. Per steradian, that's how much sky you see. Per centimeter, that's how much surface area of the star or area of your collector. So now, if I want to know how many, here, I'm going to leave that there. if I want to know, so the distribution looks like this. I keep dropping this chalk. Let's try this purple chalk again. This purple chalk keeps breaking my heart because it's really normal or really noisy. But maybe it'll quiet up. Okay. So it looks like this. This is a function of lambda. This is the energy per time per second, or per second per steradian per centimeter squared per centimeter. Maybe this is angstrom, depending on what kind of frequency you're looking at. And this curve has a peak. What's the peak? The peak you can find pretty easily. The max wavelength is just the temperature divided by 2.9. It's 2.9 millimeters over the temperature in Kelvin. So that's the peak of the thing. One of the nice bits about the black body is the curves don't intersect each other. So if I can pick 2 points, then I know exactly what curve I'm on. If I know the ultimate normalization of everything, I only need one, but I don't actually have that much information. I just need to pick 2 points here and here, and that will tell me what the temperature is, because this nested family of curves doesn't ever cross, so I just need to know what the value is, and I know which curve I'm on. So that's pretty nice. It's got a peak that I know about. It's 2.9. Now say I want to know, here's the important question, how many ionizing photons do I have from my star? So a star is a black body plus an atmosphere to first order. So we think about stars as black bodies, but then there's some other stuff, so you can't really think about it like a black body. So we'll call them black bodies, but keep in the back of your mind that there's something else. So we treat our stars as a black body. So if I want to know how many ionizing photons I get off an O star with a temperature of, say, 20,000 Kelvin, I'm not actually going to do this. I'm going to do it in pictures. I first start off with a black body at 20,000 Kelvin. And this is a function of wavelength. And this is ergs per second centimeter cubed steradian. So if I want to know how many ionizing photons I have, I got to say, well, okay, first, what's the ionizing photons? What's an ionizing photon? What's the energy of an ionizing photon? Ooh, what do I mean by ionizing? Ionizing what? What's that? Hydrogen. That's what the universe is made out of. It's all hydrogen. So when I say ionizing, I mean ionizing hydrogen. What's the energy that you need to ionize hydrogen? 13.6 electron volts. So that's how tightly an electron is bound to an atom. So 13.6 electron volts is h nu, the energy of the photon, or hc over lambda. Nu is just c over lambda. So lambda, the ionizing wavelength, is going to be 13.6 electron volts divided by hc. So this gives me my ionizing wavelength. So if I want to know how many ionizing photons I have, I just say, well, okay, here's that ionizing wavelength. Do I need to go south or north? Do I want shorter wavelength photons or longer wavelength photons? Shorter wavelength. I want the ionizing photons, so I want the shorter wavelength photons. So I want how many these are. I want everything in here. So if I want to know how many ionizing photons I get, it doesn't erase very good either, man. It's purple chalk. I want it to work. it's just going to be the integral from 0, because that's the shortest wavelength you can have, to, what did we say? 13.6 over hc times the black body at 20 Kelvin lambda. This just gives me the total number of photons that I have in this band. I've got a distribution, I integrate, I get the total number. Now, let's look at what I got units-wise. Units are very important. You can solve 80% of every problem you run into just by looking at the units. So the units are erg per second per centimeter squared per steradian. So if I want the total number of ionizing photons that are coming off of one star, I need to do this integral, but then I also need to do an integral over the area of the star and the total amount of the sky that each point of the star can see. So this is, which is a solid angle. What's a solid angle? A solid angle is a 2D angle. So an angle goes like that, a solid angle goes like that. So a solid angle is a 2D angle. It's an angle times an angle, which still has no units, because an angle doesn't have any units.
Like a cone.
Like a cone, yeah. So you got to integrate over the cone, and this cone is going to be half the sky, because the surface of a star can see half the sky. Can't see the sky that's inside the star. How many steradians are in a sphere? 4 pi. So there's 2 pi steradians here. So this integral usually just gives you a 2 pi. So I got to integrate over the area. I got to integrate over the steradians, and this one I got from this integral. So if I do these 3 integrals, then I get the total number of ionizing photons coming off of an O star. Does that make sense? Okay. I think I said more than I normally do there. Is that everything I want to say? Okay. Does anybody have any questions about the black body? We'll have more time for more questions later. Yeah.
I might have missed this, but why do we only take the ionizing photons and not the whole spectrum?
Well, because that's all I cared about for that problem. So for that problem, I want to know, say, are the O stars responsible for this big bubble of ionized hydrogen? So then I need to know, do I have enough ionizing photons to ionize this whole bubble? And the answer is yeah. So another question you could say is, how big is an ionized bubble based on some O stars? So I'll say I've got an O star, and it spits out this many ionizing photons. That means my sphere is going to be this big, however big that is. You might want all of the photons that are in the radio. So there are lots of different things that you might ask out of this. Now, if I integrate everything, so here I'm integrating from just for the ionizing photons. What happens if I integrate everything? Then I'm left with the Stefan-Boltzmann law. So I do an integral of this over solid angle, over area, over wavelength. You can look up the wavelength integral. It's not hard. It's not hard. It's calculus. Do that integral, and you're left with 4 pi r squared times this number that comes out, which is a combination of all these h's and c's. Where'd it go? Oh, here it is. The combination of h's and c's and k's and stuff. So all the numbers that come out of that constant all go into the Stefan-Boltzmann constant. So the luminosity that you have off an object that has a size r and a temperature T is going to go like r squared T to the 4th. So this is called the Stefan-Boltzmann law. So this is, if I have a thing with a temperature T, this is how many photons I get off of it. Then I use that to determine distances. So this luminosity is what I put in the top part of my favorite equation. There's like 40 things that I'm going to say are my favorite equation, but this is one of them. So this luminosity is what you put in the top part of that. So then if I want to know how far away the star is, I measure the flux with my telescope, And that gives me the luminosity over the distance. Since I know the luminosity, it gives me the distance. That's going to be a running theme throughout here. How am I doing? Oh man, I only got 15 minutes left. Okay, a black body fails when you don't have equilibrium. So something's on fire or burn or explode. No, fire is fine, but explosions aren't. So something that explodes, if there's some crap in the way like dust, that's going to be a running theme. It's going to make it not look like a black body. So we have this picture here where I've got some gas that has some temperature and then some other source that's reflecting off that gas. If all you see is the gas, then you see a black body in emission. If all you see is the reflection of the hot thing off the gas, then you see a reflection spectra. That's not a black body. It's going to come from whatever this star is. If I have this gas and I have some radiation passing through it, it can absorb a black body too. So you can see the absorption spectrum. Those are harder to do, but very useful. Okay. So line radiation, whenever I have the changes between two quantized energy levels, there's lots of ways this happens. The hydrogen atom is our favorite cartoon example. But if I have a carbon monoxide atom, that can rotate. That rotation is also quantized. So as it spins a little faster, as it changes rotation speed, it will give off a photon. So there's lots of things that are quantized that will give you photons at specific frequencies. The important bit is the spectrum is a delta function at the gas, and then you have thermal motions that can broaden that spectrum, and you have bulk Doppler motions that can change that spectrum. So if a cloud has a temperature, it'll have a distribution that's kind of broad. If it's coming at me, it'll have a distribution that's kind of broad and shifted. So the Doppler shift is given by the frequency shift is just the velocity shift over c. This is the non-relativistic version. That's the only kind we're going to use right now. So here is, and I showed these the other day. So here is the distribution. Again, this is the distribution. This is going to be in photons per second per wavelength because it's a distribution over wavelength. Here, it's all contributed. Or it's all at one particular wavelength. Here we have something that has a temperature and one that's moving. So if this is all I get out of an object, I can tell you that this object has two components. So some of the useful lines, the Balmer lines are the n larger than 3 down to n equals 2 hydrogen lines. And they're a couple hundred nanometers. H alpha, I don't know why that got typeset bad. Let's fix that. H alpha I'll talk about a lot. This is the 3 to 2 transition in neutral hydrogen. Of course, it's neutral hydrogen, it's got an electron. So we'll talk about H alpha a lot. When my kid asks me what my favorite color is, I tell him H alpha. At 656 nanometers, it's a beautiful crimson. Lyman alpha is a lower energy transition, also super important. So we'll talk about those. There are also molecular lines like the carbon monoxide rho vibrational lines and the 21 centimeter line. So there's a lot of useful lines that will show up in our time together as well. Right there. Oh, this is an annoying thing. H1 is neutral atomic hydrogen. H2 is molecular hydrogen, and H2 is ionized hydrogen. I'm going to say H2, and it's up to you to know what I'm talking about. I'm going to try to be a little bit more useful than that, but this will tend to come out. I will say, here's a big cloud of H2. And if I'm talking about star formation, it might be either ionized hydrogen or molecular hydrogen, depending. I'll try to be as unambiguous as possible, but sometimes I forget to be unambiguous. So this is spectroscopist notation, this Roman numeral. So on iron 15, how many is that? How many electrons are on iron? 26, I think. You take off 15, so there's like 10 left. Was that? 11? Thanks. Um, it's 26, right? I should know that. Okay. OBAFG. There's a dumber mnemonic for that is the one that still always.
or something.
Yeah.
Boy, and after it kills me.
What's that?
Oh boy,
Boy, and after
great.
it kills me.
Oh, that's a good one.
That's-
That's a good one. I like that. So anyway, this is the order of stars in order of decreasing temperature, mass, size, and luminosity. Temperature, mass, size, and luminosity are all related on a star. Bigger star, more bright, more mass, more size, everything. And this is what cartoon spectra of those look like. So what do you notice? So this O star goes like this, has a buttload of stuff at these short wavelengths. And this M star goes like that and has no photons at those short wavelengths. So you can tell a lot about the spectra, about what's in the star from the spectrum. We'll talk more about each one of these things. So why does it go in that order? So this ordering is dumb. This is one of the many things in astronomy that, because we've been doing astronomy continuously for the entirety of human existence, we are trapped with some old baggage. This is some old baggage. It's the strength of the hydrogen beta line. So this is one of the low energy transitions. If the star is too hot, so think about what I want to see. Hydrogen beta is the 3 to 2, is that right? Transition. I think, anyway. It's a 3 to 2 transition in hydrogen. So you need to have hydrogen in that state. If it's too hot, all the hydrogen is going to be ionized, and you can't see that line because you can't ever get hydrogen into the 3 state to make it go to the 2 state. It's all ionized. So if it's too hot, you don't see this line. If it's too cold, it's not hot enough to excite that line, so you can't see it. So we have this very nonlinear physics that we tied our scale to, and sorting everything out took a minute. This is what it looks like. I really like this picture because it really shows off what's going on. This teal one is hydrogen beta. And so the ordering is A, B, C, D, E, F, whatever, ordered based on the strength of this line. But that doesn't tell you anything about the mass of the star. This comes from when people had no idea what was going on and were just looking at stuff and writing down what they saw. And we're kind of stuck with it. But this image will show up again. So these low energy stars don't have enough to really excite this line. Like these guys can't excite that line. This guy doesn't excite that line because there's none left because it's too hot. But in here, that line is very thick and broad. So here's some numbers. O stars are like 30,000 Kelvin. The sun is a G star. It's like 6,000 Kelvin. Here's some more information. I'm just going to go past that because I want to get to more complicated things in a second. So O and B are ionizing stars. These are kind of what you need to know. O and B are ionizing. They give off photons. The fact that there's UV photons is really important for lots of things, as you'll see. F, G, and K are where most of the mass is. There's not a lot of mass in massive stars because there aren't a lot of massive stars. And then L, Y, and T are brown dwarfs, and there are some room temperature brown dwarfs. They're very cool objects. Hard to find. The third closest star to us was just discovered in like 2004. Would you think we would know about all the stars that are close to us because it's a brown dwarf and it's hard to see? Okay, we have these scaling laws. I'm running out of time, so I'm just going to point at this. Go read this slide, please. Get your head around it. So this is the relationship between the size, the lifetime, and the luminosity of stars versus the mass. Now you can derive all of this, all of these relationships, but I'm not going to because that's about way outside the scope of the class. So the size goes up like the mass to the 0.7. The luminosity goes up to like the mass to this larger power that kind of changes with mass, kind of a broken power law. But it's like 5 or 4. the luminosity goes up like the mass to this mass squared, and the main sequence lifetime is like the mass to the like 5/7. This is actually a terrible fit. This one here is a much better fit to the lifetime. So in the homework, I'm going to ask you about these things. It's on this slide. So this one is a little bit more complicated. It's the log of the main sequence lifetime in gigayears is some constant times the log of the mass times the log of the mass squared, or plus the log of the mass squared. So it's a little bit better fit. Let's see, better approximation. Pardon me, let me collect my thoughts. Okay, the initial mass function is another distribution. It is the distribution of stellar masses at their birth. And I think this is probably the last thing that I'm going to be able to talk about today. I'm not going to get the color or filters. I'll have to do that. So, okay, I need to know how many of what kinds of stars there are. I need to know how many O stars there are, so I know how many ionizing photons I get. I need to know how many G stars there are, so I know how much mass there is in the galaxy and stars. I need to know how many of which kinds of stars there are, so I need to know the distribution of stellar masses. Now, the mass of a star changes over its lifetime. They fart out stuff and blow winds, and stuff leaves. Sometimes they can lose like 80% of their mass in winds. And so after the planetary nebula phase, most of a 2 solar mass star is gone. So the mass changes with time. So that's why it's the initial mass function. How do you measure that? That's hard. Let's not get into that. Let's say that I got a cluster of stars and I know their masses at their birth. I can sort it out because I understand stellar evolution. Don't worry about that too much. So what this is, we're going to say, I'm going to write this in kind of an annoying way. I'm going to write this as dm up here. Nope. N is the number. The m is the mass. Why did I write it as little d's? Because it's a distribution. And what a distribution tells you is how many bits you have in this little infinitesimal window. So it's all about little infinitesimals, is what a distribution is. So this is the number in a mass bin, and it looks like this. It's a power law. dn dm. Now, I write it like a derivative. It's kind of like a derivative, but think about this as tiny little number and tiny little mass bin. dn dm is m is proportional to m to the minus 2.35. So what does that mean? If I want to know the total number of stars in the system, okay, the book does this a little differently, and I forget which way it does it. I think it normalizes the distribution, but maybe it doesn't. So my apologies if the book does it a slightly different way. The literature hasn't converged on the best way to call this thing. So the number of stars is the integral from 0 to infinity of the mass distribution, dn dm dm. So I'm calling dn dm the IMF. So if I integrate this over m, I just get n. Right? That's how math works. If I integrate the derivative, I get the thing. So the total number of stars is this. The total number of stars between 2 points. Say I want to know the total number of O stars. I'm going to draw this like this. Not a hard cutoff, but there is some upper mass. So if I want to know the number of O stars, I would say let's get the integral from 8 solar masses to infinity of dn dm. that'll give me the total number between 8 solar masses and infinity. If I want to know how many G stars there are, then I would go from 1.1 to 1.2. I don't actually remember what the mass range on G stars is, something like that. So if I want to know how many of what kinds of stars I have, I can use the mass function. This is very important because if I want to know how many ionizing photons I have, I need to know how many O stars I have. I know how many ionizing photons I have from one O star. Then if I have a bunch of O stars, then I know how many ionizing photons I have from those guys. Or, if I want to know how many metals there are in the universe, I need to know how many O stars. O stars blow up and give me metal. I wonder if I hope there are O stars named after Ozzy Osbourne, because he gave birth to metal too. So if I want to know how many O stars there are so I can understand all the metals, then I would do a similar kind of integral, and then I would multiply by how much metal I get for each O star. If I want to know the total mass, what do? Say I want to know the total mass in O stars. I'll go from 8 solar masses to infinity of the mass times the number I have in each mass bit. So this is m, and this is the mass, and this is how many of that mass I have. So this will give me the total mass in O stars. So the initial mass function is going to crop up from time to time, and is useful, is also on a homework. This is one of those homeworks that everybody gets wrong. So this is how you do that one when you get to it. I think that's all the time I have. Does anybody have any last minute questions on anything? All right.
Is that alright if for like 2 seconds you just take a look at like my submission on my laptop?
Oh, sure, yeah.
Yeah.
I don't know if you got any internet down here, though. The internet in this room is awful. See, we will stop the recording.